Okay. So far we have discussed about Fourier transform. So, we have got some idea about the Fourier transform pair, how they are being generated, and we have started giving some physical interpretation into this particular, after doing Fourier transform whatever we get, this GF. So, what we have seen that by analogy, because the derivation was done through Fourier series. So, we could see that there was a relationship that dn was nothing but that del f into g n del f, right. So, this is something we have got. D1 was a very important parameter in Fourier series. So, it was actually giving the spectral amplitude as well as phase of every frequency component. Now, we have seen because the del f's are becoming very small. So, we actually start getting frequency component at almost every frequency. So, it is becoming continuous in frequency domain. Earlier it was discrete, it was at first harmonic, then second harmonic and third harmonic. So, what is now happening, we are almost getting every harmonics, but because the del f is very small. So, we are almost getting every frequency component, which we have already. So, if I just see, so what was happening as del f was tending towards 0. So, we were getting very closely packed values. Okay. So, almost continuous values. So, earlier whenever we have plotted spectrum, it was like this. So, there was some strength at different frequency f0 to f0 and so on, and the corresponding values was dn. Here what is happening, that dn is just not this g, it is actually g into del f. So, it is almost like this box integration. Okay. And on top of that, as del f goes to 0, these are becoming closely packed. Okay. So, once they are becoming closely packed, basically I am getting a continuous spectrum and the corresponding dn's are getting vanished, okay, because it is multiplied by del f. As del f becomes smaller and smaller, corresponding things are becoming vanished, but the dn might vanish, but the g still has a relative strength. So, what it says, almost like if g multiplied by the frequency, I get the corresponding dn, okay, and we have already seen that integration gives me some value. So, basically this g by itself is not the spectral component, it is defined as per unit spectral, because the del f has to be taken out of it. So, it is the overall integration that gives me the spectral component, let us say the amplitude, that is given by, if I just multiply it by del f. Okay. So, if I just divide this gn by del f, dn by del f, then I get this g value, right. So, basically it is, this g is nothing but the spectrum component per unit frequency. Okay. So, whatever that del f is per unit frequency in a very closely packed frequency domain representation, I get that at instantaneous frequency what is the per unit frequency spectrum component, okay, or the spectrum strength. So, that is why whenever we talk about g, it is not the spectra itself, it is actually the spectral density. Earlier when we were plotting dn, we were saying that frequency component is having this much amplitude spectrum, or this is that particular frequency component is having whatever modulus dn is this much amplitude. Now, we are not saying that, we are saying per unit spectrum, okay, because it has to be divided by del f, this is the amplitude strength. So, basically what is happening, suppose I take a gf value at a particular frequency and I take another gf dash at another frequency. So, it is actually their relative spectral strength, actual spectral strength, if del f is tending towards 0, is 0 for both of them, but the relative nature is still being intact. Gf and g del f dash will have a relative strength to each other, but their actual strength, if you wish to calculate, that must be multiplied by del f, then only we will be getting the equivalent value with respect to dn. Okay. So, once I do that and del f tends to 0, I do not get anything. So, that is why whenever we talk about this GF, it is actually a spectral density, not a spectrum itself, whereas in Fourier series whatever we are getting, that is actually a spectrum, because there the individual value that we are getting, that is a real value, and that value just specifies in that frequency component how much strength it has, whereas here I have all the frequency component, it is continuous. So, because I have every frequency component, each individual component, like that example I have derived, that each individual component does not have a probability value. So, if I say 30-degree angle, when that pivotal rod will stop and what is the associated probability, that probability value will vanish, that will be 0. Here also same thing, what is the spectral strength of 5 kilohertz? If I say that will be always 0, the answer will be that 5 kilohertz, be it 10 kilohertz, be it 5.5 kilohertz or 5.6 kilohertz, everywhere the actual spectral strength is 0, but there is a relative strength between them and the spectral density is well defined, which is G. G is defined and that will have relative nature. So, G at 5 might not be same as G at 10. So, they might be different, but if you just ask what is the spectral strength at 5 and 10, it will be all 0, because by definition the G which we have evaluated now, you can see that that is giving me spectral density, not spectra. So, this is something why I am repeating again and again, because this is very important. You need to understand that whenever we are plotting this GF, it is not giving me the actual spectrum, it is spectral density. We are plotting actually spectral density, and the difference between a energy signal and periodic power signal. In periodic power signal, we take Fourier series, and each frequency component that we represent over there gives me exact value of the amplitude and corresponding phase of that frequency component. Here in the spectra, so that is why that spectra is discrete spectra. It has some values where it is defined and all other values it is not defined, and at every value you have a definite finite spectrum strength, or I should say the amplitude of that particular frequency. Whereas in a Fourier transform, where we are representing energy signal or time bounded signal, we have every frequency component. So, we cannot discriminate that this frequency is there, it is a continuous thing. With frequency, whenever we plot, it is a continuous thing, and the corresponding GF that we plot, it is not spectra by itself, because at a particular frequency the height I will be getting, that is actually not the spectral strength, because spectral strength is that at that particular frequency the value GF into some del f which tends to 0, because it is a continuous. So, the del f goes to 0. So, basically the spectral strength will still become 0, whereas what we get is that spectral strength divided by del f, that means spectral density per unit frequency, how much it has, that is something that we get. Okay. So, GF defines that. So, that is where these two particular spectrum has slight differences, and you have to be very careful about when you are generally talking about these things. Often we do that mistake, and in many books also you will see that they just represent it as spectrum. So, they said for a particular time bounded signal I do Fourier transform and then I plot GF, that is actually my amplitude spectrum. It is not, or modulus GF I draw, I get amplitude spectrum. It is not, it is spectral density, it is no way spectrum, because the spectrum is GF into del f, which has no value. It will be 0 everywhere if I try to plot that. It is just the density which has some meaning over there. In a way it is meaningful, because the signal that we are seeing, that is a finite energy signal, right. We are now representing it into frequency domain. If in the frequency domain every frequency component has some finite value, and then there are frequency components which are infinite in number because it takes continuous values. So, every frequency value it takes. So, then overall energy will be infinite. So, it should not be that way. It should be each individual component should be still 0. Only thing is that spectral density it has some value, so that I integrate from one particular frequency to another frequency. That means I take the area which is actually the energy, that will have finite value. So, the integration will still have a finite value, but individual one will not have any value. So, this is a very important concept which you should be able to always remember. Okay. So, whatever it is, now what we have done is we have understood what is Fourier series and what is Fourier transform, how we get Fourier transform out of Fourier series and what is its significance. So, for any signal GT, we have also got these two relationship, that one is this GF which is Fourier transform, it is GT e to the power minus j 2 pi ft dt integration minus infinity plus infinity, and we get inverse Fourier transform which is minus infinity plus infinity GF e to the power plus j 2 pi ft df. So, this is in frequency integration, we get back our time domain signal. This is the time integration, from the time signal we get the frequency representation of it. Okay. So, this is something we have now identified. Now, what we will talk about why we are doing all these things, because this has a huge implication in communication. You will see that every part of communication techniques that has been derived, that has some root in Fourier transform or Fourier series. You will see that, means we will one by one derive all of them, and you will see that this understanding is pretty much essential for our overall understanding of communication technique. So, what we need to now do is try to get some very important property which are particularly in use for communication technique. So, that is something we will be now dealing with. So, before that, let us try to see whatever happens in Fourier series, that it is a event symmetric spectrum and all those things. Let us try to derive that part also. So, we are trying to derive this complex conjugate of GF. What do we get? So, GF, just write the expression of GF and we will take complex conjugate. So, that is GT e to the power minus j 2 pi ft dt integration minus infinity plus infinity, we take a complex conjugate of this. Now, as long as my GT, that signal that we are targeting to get Fourier transform, is real, if this is real, then if I take complex conjugate, because integration has nothing to do with conjugation, so conjugation will come inside, then it will be distributed over these two. GT is complex conjugate because it is real, so that remains GT. So, we get minus infinity plus infinity GT and the complex conjugate of this. So, that should be it is plus j 2 pi f t dt. Okay. So, what is this? Let us rewrite this in a different fashion. So, we write GT e to the power minus j 2 pi minus f t dt. Okay. Now, if you see this is almost like a Fourier transform, GT into e to the power minus j 2 pi, there is something into t dt. So, this is actually, if it was f, it could have been GF, because it is minus f, this must be G minus f. So, if you now see, it is almost giving similar result as Fourier series. So, d minus n, if you do complex conjugate of d plus n, you get G minus n, d minus n, same thing is happening. For a particular frequency f, if I do complex conjugate of GF, I get the negative of that. So, basically it says that spectrum also, if I take amplitude spectrum, it will be event symmetric, and if I take phase spectrum, if GF is complex, then I will get, because the complex conjugate is just negative. So, I will always get a odd symmetry in phase. So, this will also have, if you clearly see, GF, if it is complex, it will have amplitude as well as it will have phase. So, it will always be having two spectrum, one is for amplitude, one is for the phase. Okay. So, we are saying this is spectrum, this is again you have to remember that it is a colloquial term what we use generally, but it is no longer, as long as we are talking about energy signal, we are not talking about spectrum, it is spectrum density. Okay. So, now let us try to derive few Fourier transform pairs. Okay. So, let us say if I have a signal e to the power minus a t u t, we have already defined u t, it is up to from minus infinity to 0 it is 0, and then from 1 onwards 0 onwards it's actually its value is 1. Okay. So, this signal we want to get the Fourier transform of that where a is greater than 0. Let us just do it in a very simple manner. So, we want, suppose this is g t. Okay, so, we want to evaluate g f, which is nothing but minus infinity to plus infinity, or g t into e to the power minus j 2 pi f t dt. Okay. Now, g t, because of u t, it is defined from 0 to infinity only. So, this integration minus infinity it will be all 0, minus infinity to 0 it will be 0. So, it should be evaluated from 0 to infinity. Now, g t becomes e to the power minus a t, because u t greater than 0 it is always 1. So, it will just give me this value e to the power minus j 2 pi f t dt. Now, let us evaluate this. So, it is just an exponential e to the power minus a plus j 2 pi f into t dt. So, that should be minus 1 by a plus j 2 pi f, right, putting value 0 and infinity. At infinity, if I put f equal to infinity, this goes to means 0. So, we do not have a value. At 0, I will be getting, see, for t of course, it should be, wait a second, I have not done it correctly, that should be there. Okay, yeah, 0 and infinity. So, if I put infinity, this becomes 0, right. So, this is the integration 1 by that coefficient e to the power minus j, of course, that a should be there, sorry. Okay. So, if I put t equal to infinity, what happens, this goes to 0, because e to the power minus infinity. So, that goes to 0. So, that whole value will be 0. When I put t equal to 0, so this becomes 1. So, it remains as this. So, because it is minus, so that minus will be cancelled. So, this becomes a plus j 2 pi f. So, as you can see, for a signal g t like this, our g f becomes 1 by a plus j 2 pi f. It is a complex signal. Okay. So, we have evaluated this. Good. The next part is we will try to evaluate some other things. So, let us try to see if we can evaluate another very important signal. So, we will use this part to evaluate that is called signum function. So, what is actually a signum function? A signum function is something like this. It is almost like u t, but it has something in the negative. So, basically it is 1 in the positive half, it is minus 1 in the negative half. So, it is defined as this. So, if I say signum of t, that is actually plus 1 whenever t is greater than 0. It is at this point it gets a value 0. So, this is open. This is a discontinuous function of course at t equal to 0, and this is minus 1 t greater than 0. So, if you wish to do a Fourier transform of this signum function, you will see that we will have a technique called single sideband modulation, where signum function is a very important function, you will see, and that is why we are doing this Fourier transform. So, it is very important that we understand the Fourier transform of this thing. How do we evaluate this Fourier transform? So, let us try to see. Directly you will not be able to evaluate this. If you just put it this way, you will see all kinds of infinity coming up. Directly we will not be able to evaluate this, but we can evaluate in a clever way. We can represent this signum function as this. It is actually e to the power minus a t into u t minus e to the power a t into u, sorry. So, if you see what is happening, it is actually combination of these two. First is e to the power minus a t u t. What does that means? E to the power minus a t u t looks like this. So, u t means it is defined only in the positive half, right, and e to the power minus a t means at t equal to 0 it is 1, and from there it is exponentially decaying. Okay. Now, in this one, if I put a tends to, means a is just tending towards 0, if I just put that, what will happen? This particular value will almost become 1, and this will almost mimic the positive half, because this will be the slope of this exponential decay will remain as it is. So, it will for every value, because a tends to almost 0. So, this will always become 1. So, this will be very slowly decaying, and it will almost mimic these things. Okay. And this part, it is u minus t, that means it is defined over here in this range, because u t is defined from 0 to infinity, therefore, u minus t is defined from minus infinity to t, right. So, u minus t means it is defined over here, and I have put e a t. Okay. So, as a tends to 0, this will again become a value 1 for every value of t. Okay. But what is happening, because there is a minus, so it will always attain a minus, and it will be something like this. Okay, very slowly decaying. So, at if I just put some value of a, some finite value of a, okay, so then e to the power a t will be, as t increases, this will be decreasing, almost similar like this. Here from minus 1 it will be actually increasing, and at t equals to infinity probably it will go to 0. So, it will at the negative, this one it will start from minus 1 and it will go to 0, but if a tends to 0, this will almost become flat. So, this particular function, as a tends to 0, almost mimics the signum function. So, what we will do now, to get Fourier transform of signum, we will take this representation and use the previous result to evaluate the Fourier transform of signum function. So, let us try to see. My signum function has been already represented. So, Fourier transform of signum t must be Fourier transform of e to the power minus a t u t minus e to the power a t u minus t, right. So, this is our Fourier transform. Now, Fourier transform of e to the power minus a t u t, that we have already derived. Okay, e to the power minus a t u t is 1 by a plus j 2 pi f. So, this, and Fourier transform, if a function is having a linear combination, Fourier transform just gets distributed. That is very easy to prove. Just put the Fourier transform formula and you will see that if g t is represented as c1 x t plus c2 x t, the integration gets distributed. So, basically corresponding Fourier transform you can individually take. So, I can do a Fourier transform of this one, which is nothing but 1 by a plus j 2 pi f. Similarly, you can evaluate this one also, e to the power a t u minus t. So, that is very easy. If you just take this integration and replace minus t by t, okay, just take a dummy variable called z equal to minus t, it will just become this. And then if you just try to evaluate that, what you will get is this one. Take that as homework, you will be able to evaluate this from the fundamental principle, as we have derived this one. Similarly, you will be able to derive for e to the power a t u minus t. So, that is pretty easy. So, if you do that, you will be getting this. Okay. And we have to also put, now that particular part comes, limit a tends to 0. So, here we will have to put limit a tends to 0. Whenever we put this, we immediately get 1 by j pi f, because a goes to 0. So, we have this, and we get 1 by j 2, 1 by, because 2 is there. So, half plus half it will be 1 by j pi f, we get this. So, signum function, that is a very important result, even though it is a discontinuous function. it has a Fourier representation and Fourier transform correspondingly. So, signum function has a Fourier transform of 1 by j 2 pi f. Okay. So, this is again another important property. Now, the one we will be describing, probably that is the most important property of Fourier transform, which has been used heavily for communication. This is called frequency shifting property. What it is? Let us try to see. Suppose I have a signal GT. I already know the Fourier transform of this. So, I have a known signal, let us say that is GT, and I also know its Fourier transform, let us say this is GF. This is something we know already. So, this pair we have already evaluated for some means, by means of Fourier transform only we have evaluated. So, this is given, suppose. Now, we are trying to prove that if this signal GT is multiplied by a exponential e to the power j 2 pi f0 t, if that happens, the corresponding Fourier transform will be just, that is why it is called frequency shifting property. So, it will be just, the spectrum will remain the same, it will just in the frequency domain translated by a amount f0. So, this is something we wish to prove. That is a very simple way of proving this. So, suppose we know GF is equal to minus infinity to plus infinity GT e to the power minus j 2 pi ft dt. So, this is something we know. Now, we want to take Fourier transform of this one. So, therefore, we have to do let us denote that as G dash f, that should be minus infinity to plus infinity GT into e to the power j 2 pi f0 t e to the power minus j 2 pi ft dt. So, that should be the Fourier transform. Let us try to evaluate this. So, minus infinity to plus infinity gt e to the power. So, if I take just this minus j 2 pi t common, so we get f minus f0 dt, right. So, that is my g dash f. Now, if we assume, see what was happening, my Fourier transform, if GT has a Fourier transform e to the power j 2 pi f into t dt, then I get GF. So, if I just replace f by f minus f0 or a new variable. So, therefore, from that analogy I can get this is equal to g of f minus f0, which is nothing but gt f minus f0 dt. So, this is something I get. So, immediately I can write that g dash f is nothing but this. So, I can see that if I know, see gt into e to the power j 2 pi ft dt, that is gf. Therefore, gt e to the power j 2 pi f minus f0 t must be g f minus f0. This is very obvious because it is just a function of whatever is there over here. So, it is becoming just that function. So, what we are seeing that if we multiply a signal with e to the power an exponential e to the power j 2 pi f0 t, that corresponding frequency f0 is just translate the spectrum to that particular part. Okay. So, this is pretty understandable. Now, what we will do, we will try to see why exactly this is a very fundamental property for communication in the next class.